So the next speaker for today is Niccolò Veltri, and he will talk to us about proof theory of partially normal skew monoidal categories.
Okay, thank you, Christina, for the introduction. I would like to add also that this is a joint work with Tarmo Uustalu and Noam Zeilberger. It is indeed a proof theoretic investigation of something called skew monoidal categories with some partial normality condition. So what are skew monoidal categories? So this is a notion that is due to Zlakani in 2012. And it's a weakening of a notion of a monoidal category. So we have a category C with a unit and a tensor, and three natural transformations, so two unitors and an associator, satisfying five coherence laws. So these are the five laws of McLean. But the main difference between this and the usual definition of monoidal category is that we have natural transformation. Oh, sorry, it's natural transformations instead of natural isomorphism. So we don't require the unitors and associator to be invertible, but they are just natural transformations pointing in a particular direction. So in this situation, they point like this. So lambda goes from I times A to A, rho A goes from A to A times I, and alpha associates the brackets from the left to the right. Okay, one can, in principle, also ask for some of these structural laws to be invertible, and these are what we call normality conditions. So when we talk about left normal skew monoidal categories, if lambda is invertible, we talk about right normal skew monoidal categories, if rho is invertible, and finally we talk about associative-normal skew monoidal categories whenever alpha is invertible. And one can clearly recover the usual notion of a monoidal category by requiring, by taking skew monoidal categories satisfying now all the three normality conditions. Now there are many examples in the literature, and these things have been heavily studied in the past, let's say 8 years. Or so, mostly by the Australian category theorists, so Street, Lax, and colleagues. And they appear in the study of programming language semantics. So for example, in the study of relative monads by Altenkish, Chapman, and Uustalu, and also quantum categories by Street and Lack. So I don't have much time here to show you examples, but only one, I'll show you only one. So if you have two categories, J and C, and a functor between them, then you can you have a skew monoidal structure on the functor category between J and C as follows. So the unit is the given functor J, and the tensor of F and G is the composition of G with a left-hand extension of F on J. So we assume that this left-hand extension exists here. And one can check in this case that lambda, rho, and alpha, the structural laws exist. It's possible to construct these morphisms, but without asking any additional structure on the functor J, there is no way of defining the inverses of lambda, rho, and alpha. Okay, so this is kind of a skew variant of the usual monoidal structure on the category of endofactors on a given category. Okay, so what is the story here? So in previous work, so a couple of years ago, we presented a sequent calculus for skew monoidal categories. Precisely, this means that this is a calculus that is a presentation of the free skew monoidal category on a set of generating objects. And we showed that this calculus has some nice properties, so it enjoys cut elimination, and it admits also a focus subsystem of canonical derivations. And here we continue on this line of work, where we develop sequent calculi for partially normal skew monoidal categories, where now partially normal here means that one or more normality conditions are enabled. And we prove cut elimination, we show the calculi admit focusing, and what we obtain in the end is a family of sequent calculi that sit between those of skew monoidal categories and the one of monoidal categories, so the fully normal monoidal categories, which is actually due to Lambeck. And at the level of derivability, we define 8 weakenings of the multiplicative fragment of intuitionistic non-commutative linear logic. So when we only have two connectives here, so unit and tensor. Okay, so the talk will be basically split into parts. So first, let me recap what was done a couple of years ago. So what is the sequent calculus of skew monoidal categories? And in the second part of the talk, I will start talking about partially normal skew monoidal categories. Okay, so this is the sequent calculus for skew monoidal categories. So formulae are generated by this grammar here. So they can either be a unit, a tensor, or they can be an atomic formula, or we usually use X, Y, and Z in this SOP for representing atomic formula. So we are given a set AT of atoms. And now the interesting part is here. So sequences are a bit different from the usual notion of a sequence, for example, in intuitionistic linear logic. So we have triples. These are triples. So the succedent is a single formula, C, but now the antecedent is split into two parts. So there is a gamma, which is a list of formulae. We call it a context. So but it's an ordered list of formulae. And then there is a stup, S. This is some terminology from linear logic. And this is an optional formula. So it means that it's either a single formula or it is empty. So we distinguish here between a situation where the stup is empty or it contains a formula. Okay, and the rules of this sequent calculus are these 6 rules. So we have an axiom rule, so we can derive A from A. And A here is in the stup, the formula is in the stup. Then we have 2 left rules, one for unit, one for tensor. So in the left unit law rule, we can see that we are able to, if you read it bottom up, we are able to remove a unit from the antecedent, right? So this is the notation, this line here is the notation that we use for indicate that the stup is empty. So we can remove a unit from the antecedent provided that the unit is in the stup. So we do not allow general left unit rule that in which the unit can be removed if it appears in the context gamma. So we don't have that. And we have a similar rule for tensor. So we're now again, so the tensor can be decomposed from in the antecedent if it sits in the stup position. And then A, after that, A will be in the stup and B is moved to the context. There are also right rules. So the unit right rule is kind of the same as for the case of monoidal categories. So we can only prove unit if this antecedent is empty. And for the tensor right rule, so as usual, for example, in the lambda calculus, we have to split the context into 2 parts. So, and the left part, the part on the left has to go to the first premise, the part on the right has to go to the second premise. But there is a novelty here, which is that the stup, so the formula in the stup, when there is such a formula, is required to go to the left, to the first premise. So it's impossible for this formula to be used by the second premise. Okay, and then there is also some rule pass, which if you read it again bottom up, it allows you to move the leftmost formula in the context into the stup position. Okay, so let's see some examples of what you can do with this calculus. So the idea here is that you get a skew monoidal category, so you should be able to derive some sequences that correspond to the unitor and the 2 unitors and associator of skew monoidal category, but you shouldn't be able to derive their inverses, and that's why we have all these restrictions in the calculus. So, for example, you can construct a derivation corresponding to lambda like this. So you apply tensor left here. This is fine because this formula is in the stup. You apply unit left, again, it's fine, and then using this pass rule and the axiom is done. But there is no way to derive, to construct a derivation corresponding to lambda minus 1. So because if X, for example, here is an atomic formula, so in here we are stuck. The only thing you can do is, in principle, to come up with a valid derivation is apply a tensor right rule. But we have this restriction in tensor right that forces the formula in the stup to go to the first premise. So now we are not able to conclude, to find a valid derivation here. Now we also have a derivation for rho, which is also relatively straightforward, but we cannot derive, we don't have a derivation corresponding to rho minus 1. And now the problem is the following. So again, if X is an atomic formula, we can only reasonably apply tensor left rule here to break this tensor. But now you have a unit in the context, and remember that our unit left rule only allow you to remove units if they appear in the stup. So now, since this I is in the context, we're not able to remove it, and we are not able to finish our derivation. And there is a similar situation for alpha. So I'm not going to do this derivation. So one can pretty straightforwardly derive, have a derivation corresponding to alpha, but there is no way of deriving something, deriving alpha minus 1. And now the problem is that at some point you will have a tensor in the context and you're not able to decompose that because the tensor left rule only allow you to decompose tensor if it appears in the STU position. Okay, so then one would like actually to also, of course, derive to prove that the coherence law, so the equations of a skew monoidal category holds. But for that, one has to come up with an equivalence of derivations. So we have to identify some derivations. I'm not going into details here. So we have these 5 equations. There were 2 eta conversions, which expand the axiom rule on identity and tensor. And then we have some commutative conversions that tell you that the tensor right rule commutes with the other left rules and pass rule. Okay, once you have done that, these are the results that we have. So first of all, you can derive 2 forms of cut. So these are cut is admissible in 2 forms. And why 2 forms? Because the substitution can happen either in the STU position or in the context position. Okay, so that's why you have these two cut rules. And moreover, one can prove that the sequent calculus that I've shown you is when now the derivations are quotiented by this equivalence of derivations. This is a presentation of the free skew monoidal category on the set of AT of atomic formulae. And clearly, this cut rule is used for modeling the composition. It's the composition of this category. And we have also another result. So we have also an equivalent focused sequent calculus, in which now the derivations are canonical representatives of equivalence classes of this equivalence relation. So which means that we have only the derivation in this calculus are in normal form with respect to this equivalence relation. And in fact, there is a bijection now between the derivation of a sequence in the focus sequent calculus. So this is the syntax that we use for sequence in the focus sequent calculus, and derivations of the same sequent in the unfocused sequent calculus up to this equivalence relation. So what the focus calculus does is it defines a root first proof search strategy that tries to build the derivation. But unfortunately, I don't have much time to talk about it. And also, this is a very concrete. The focus sequent calculus is a very concrete description of the free skew monoidal category, and as such can be used to solve the coherence problems for skew monoidal categories. Okay, so now let's move to the second part. So now we start talking about partial normality. So we'll see the three cases. So for left normal, right normal, and associative normal. So what we're trying to do is obtain sequent calculus in here, for example, for left normal skew monoidal categories. So remember, left normal means the lambda is invertible. So and the sequent calculus would be the same as before, plus an extra rule, which is a new tensor right rule, in which one finally is allowed to move the formula in the STUP to the second premise, provided that the whole antecedent is moved to the second premise. So the antecedent of the first premise is required to be empty. Plus then one has to identify more derivations in this equivalence relation. And using this rule, one can construct lambda minus 1 in the following way. So you just apply this new tensor right rule. Now the whole antecedent can be moved to the right, to the second premise, sorry, and then you can conclude. Interestingly, in this calculus, the pass rule is invertible up to this equivalence relation. So there is a rule that read bottom up now allow you to move the formula in the STUP from the STUP to the context. And what this entails, moreover, is that the left normal sequent calculus, so the sequent calculus of left normal skew monoidal categories, admits an equivalent STUP-free presentation. So similar to closer in spirit to the sequent calculus of monoidal categories, for example. More interesting is the situation of right normal skew monoidal categories. Well, remember, right normal means the rho is invertible. So in here, the sequent calculus will have 2 extra rules. So one for a new left unit rule for removing the unit in the context. So now you're allowed to remove units. In this calculus, you're allowed to remove units everywhere in the antecedent, so not only in the stoop. But also there is also this other rule that allows you to decompose a tensor in the context, provided that both formula J and J prime are closed formulae. So they are only made out of units and tensor. So they, in particular, they don't contain any atomic formulae. Plus, then one will have more equations here as well. So using this IC rule, it's easy to come up with a derivation corresponding to rho minus 1, because now this unit in the context can be just simply removed. But then why is this extra rule needed? So this is needed if we want to have cut elimination, because for example, in any right normal skew monoidal category, you can come up with this composite morphism. So from x times I times I into x, in which you apply a lambda here, and then you conclude with rho minus 1. But if we don't have this extra tensor left rule, there is no way of deriving a sequent associated to this type here without using cut. Because now the only sensible thing you can do here is applying tensor left rule, and now you will be stuck if you don't have this rule. And now in here instead we can decompose further because I is a closed formula, and then we can remove both units and conclude using the axiom. And finally, we have also the associative normal case, so which is the one when alpha is invertible. And in this case, we have the sequent calculus has a new extra rule, which is very similar to this. But now it's more general because it works for any two formulae, arbitrary formula A and B, not just closed formulae. Again, we have more equations, and it's easy to now to find a derivation corresponding to alpha minus 1. And now the idea is that you use the new left rule for tensor in this position here, when you just break this tensor apart in two, and then you continue pretty straightforwardly. Okay, so what are the results? So we have, so first of all, we define a family of sequent calculi because we can also combine multiple normality conditions and get sequent calculi for, let's say, simultaneously left normal and right normal calculi, Skew Monoidal category, sorry. And now for all these sequent calculi, we proved cut admissibility and focus, and they all admit focusing. And unfortunately, I don't have time to show you this, but the interesting cases are the right normal and the associative normal case where things get more involved, and we had to use some machinery from Chowdhury and Fanning in their focus linear logic paper, 2005. And finally, now each partially normal sequent calculus, now when the derivation are quotiented by the appropriate equivalence relation, this is a presentation of the free partially normal skew monoidal category on AT, when of course the degree of normality has to agree here between the sequent calculus and the free partially normal skew monoidal category. Okay, so again we get a very concrete presentation of the free partially normal skew monoidal category using the focus calculus, which can also use for solving the coherence problem. And finally, let me conclude. So first, I would also like to mention that we have a full formalization of the material that I presented here in the proof assistant AGDA that you can find in this link. So the paper, if you read the paper, there are not that many proofs because we rely on our mechanized proofs somehow. And so if you are curious, you can go and have a look in our formalization. And for the future, we'd like to extend our story to other skew variants of well-known category constructors. For example, there is a notion of skew closed, the skew monoidal closed categories due to street, which is a weakening of a notion of closed categories, for example, or monoidal closed categories. And another interesting case would be, for example, doing this for braided or symmetric skew monoidal categories, which has been recently studied by Burke and Luck. And in here you have a new natural transformation, for example, in the symmetric case, you have a natural isomorphism of this form, which is pretty interesting. It's kind of a symmetry in context. So you're allowed to swap B and C, but A has to stay still. And we believe that this can be modeled in the sequent calculus now using our stoop in a nice way. So if there is a formula in the stoop, you're allowed to move to swap any two formulae in the context, but the formula in the stoop must still stay still. Okay, I think that is it, and thank you for your attention.
Thank you very much. Let's thank the speaker. Okay, if there are any questions, you should go ahead and unmute and ask the speaker. In the chat, there was just some discussion that these rules are read from bottom up rather than from top bottom when you're explaining them. Yeah, that created some confusion at the beginning, I believe, but yeah, there it must have been pretty clear. Okay. All right. If there are no questions, very clear talk. We should thank the speaker again.
Thank you.
And we will begin again in 4 minutes from now.